Morning. Welcome to Calculus in the Air.
3.4.
Continuity of functions. So what does it mean for a function to be continuous? It doesn't have any breaks in it. Okay, that's pretty self-explanatory here. No breaks. No breaks. So you might be thinking, piecewise functions, yeah, that's where you could have breaks. Possibly. They're not always. The other ones. Infinite discontinuities. You have a vertical asymptote, where you have a situation where you get 1 out of 0. So what would this function possibly look like here? It's a 1 over something, right? Well, rational functions. This function is discontinuous at x equals 2. So that's an infinite discontinuity, and you're going to have to memorize these types. Infinite discontinuities. So sometimes you can have infinite discontinuities like this too, right? Or both going down. So here's the example here, right? Then, second type. Jump discontinuities. Piecewise functions and absolute value functions sometimes. Depends how it's built. So, I think it's pretty simple to see with the picture. Jump. You see why it's called a jump, right? Okay. Not as simple if you're just given this, but typically, if you look at the pieces of a piecewise function, if you see that something's a polynomial, like x squared plus 5, or x, in this case, a linear function or so, there's no discontinuity within this first chunk, is there? It's a line. There's no discontinuity within this chunk, it's a line.
May I have your attention, please? Sorry for the interruption.
So what do? Always then just look at where the join is. And you just plug in 2 to here. Well, this is actually where you should plug in 2, right? Because it's equal to 2 there. So the function gives you 2. The y value would be 2. So 2 comma 2. Hey, that looks like a 2. Then you pretend, if you could plug in 2 to this portion, what would you get? 3 minus 2, 1. That's this one. So without the graph, you pretend you could plug it into both portions and see, is it the same value? Then it's continuous. If it's not, you have a jump, discontinuity. The third type that we look at, removable discontinuities. And you're familiar with these from your rationals work in pre-calc 30. This is where you can factor out. When you had an indeterminate result of 0 out of 0, and we can evaluate those limits too. And you get a hole in the graph with the picture, and this is because if you factored out the numerator, x plus 2, x minus 2, you could remove the factor from the top and the bottom, and you'll have a hole in there, right? So removable discontinuity. So those are your 3 types. Be able to identify them either from equations or from pictures. And if you're just given an equation like x squared minus 5 plus 2, there shouldn't be any reason for breaks in that, right? So if you're just given equations without pictures, be familiar enough with all the different types of functions. Remember I gave you pictures of all the functions. You should kind of have them in our brains from pre-calc 30 in this class. Basically, you're on the lookout for when you have rationals or piecewise functions for those kind of breaks, right? For either any of these 3 types. The other thing you should always be aware of, though, because there's domain restrictions on even roots, square roots, fourth roots, and stuff like that. Be aware there. Now, we'd say they're continuous on their domain, but if I said, for just the simplest one, y equals the root of x, this is continuous on its domain. Just keep in mind that its domain starts at 0 and is x greater than 0, x equal to or greater than 0, right? It's continuous on that domain, even though it doesn't exist for negative numbers. And then you'll have variations of that. So that's continuous within its domain. Make sure you know that. Continuity principles. So what we were just saying, guess I didn't say this one. Constant functions are continuous. Y equals 5. Well, that's a straight line, right? At 5, y equals 5. Other functions are continuous. You come across polynomials most often. Rational functions are at every point in their domain, because you might be confused. Well, I thought you said rational functions. You got to watch for holes, possibly, like removable discontinuities, or else infinite discontinuities. Those points aren't actually in their domain, though. So this is one you really got to watch for, because there's going to be points that aren't in their domain. Power functions, x to the 4, x to the 5, they're continuous. Root functions are continuous. I just showed you square root within their domain. Trig functions, continuous within their domain, especially you're familiar with the sine and cosine, right? Continuous. Tangent isn't, because its domain, you know, tangent is sine divided by cosine of theta. Wherever cosine of theta gives you a 0 is not included in the domain of tangent. So there is actual infinite discontinuities within the tangent function at the points that aren't in the domain. Exponential functions, what do they look like from left to right? Somebody with their hand, anyway? An exponential, 2 to the x, e to the x. Well, they look like this. Do you remember that? They always cross, if it's just 2 to the x, it'll cross at 0, 1. A logarithmic function, if you graph that, its domain does not include any negative values if you're talking about just log base 10 of x. Okay. So, that's why we got to be familiar with all the types of functions in chapter 2. I had you refamiliarize with some of the functions. If two functions, f and g, are continuous, then if you add the two functions, subtract the two functions, multiply the two functions, you've got a continuous function. Here's where you got to be careful when you make a rational, x plus 2 over x minus 3. This is a rational. You can think of f of g over, or f of x over g of x. In their common domains, they're continuous, provided that, and this is what I was talking about here for the rational, you can't have a 0 on the bottom. Okay. Enough of that. Let's test this out. There is a test for continuity, and you're going to have to give me steps 1, 2, 3, or A, B, C. If I ask you, and it is definitely required, you will be tested, and you will need to you can't freestyle, you got to use these steps. Here's the 3 steps, whether you're given a picture or an equation. If the function is continuous at a point, B, so 7 or 2 or whatever. All 3 conditions are satisfied. Test in this order. First thing, the function, when you plug in B, so let's just pretend it's 3. If you plug in 3, it must exist. F of 3 must exist. So it must be in the domain. The next thing, if you take the limit, it must exist. Remember, approach from both sides. For a limit to exist, the left and the right-hand side must match. Okay, and then, third thing, in order for the continuity to hold true, the limit must give the same value as the function when you just plugged it in the first step. We'll see some things here. Which condition for the continuity at a point test is not satisfied by each? So, we're testing at x equals -1. And we're looking for negative answers because they say not satisfied. We go in order, A, B, C. Now, I'm not going to use, I'll call these 1, 2, and 3, only because this is question A, B, and C, okay? I don't care if you use A, B, C, or 1, 2, 3. It's easy as A, B, C. Easy. Okay, so let's test this out. So question A, the first thing we test, I'll use a small Roman numeral, 1. Is, does this exist at -1? Can you put -1 into this function? No. Because if you tried, we're talking about this function. Rubbish, right? Okay. No answer, undefined. I'll put undefined, it's a better word. Oh, you know what's happening. undefined. So therefore not continuous. You guys ever see 3 dots as therefore?
Yeah.
He has, okay. So I'm gonna go, therefore, not continuous. I'm gonna use, you can spell the whole word if you wish, I'm gonna use CTS, continuous at x equals -1. It's continuous everywhere else, but not at x equals -1. That's the reason. B. First thing we test. We're always testing at -1 because that's what the question asked here. And x equals -1. So does g of -1 exist? Now look at this. Use this equation when it's not -1. Okay, can't use that. So I'm using this. When x equals -1, do you have to do any calculations? No. It's just plain old 2. That's what we're saying. Okay, just give it a 2. So that's the first condition I didn't label. You don't have to label it 1, 2, 3, but I'm doing that just to show you where it's from. Got to do it in this order, though, so that the first condition is passed. Good. Second condition for continuity. Does the limit exist? The limit x approaching -1. Well, let's approach it from the right and the left, and then just, well, maybe we can do this all at the same time. We'll test it out. For g of x. Which portion of g of x would we use? Well, we're approaching -1, but we're not letting it, remember how philosophically we're not letting it equal -1. So we're actually going to use this portion because this is for everything that's not -1. That includes -1.0001 and -0.999, right? As you approach -1 from left or right. Now, x squared plus 5x plus 4. Let's save ourselves a step. Factored? What is it? You can think of it as factored. Top, the numerator, I'm factoring. 4 plus 4 plus 1, x plus 4. Is this correct? By Jove, it is. Right? Okay, good. What do you notice about this? You can evaluate this limit. Because I'm not going to, I'll just, we scratch out. So really, we could just jump right into -1 plus 4, right? So I'm going to write that down. -1 plus 4, 3. So the limit exists. Third condition. From the left or the right, it's true. What was the third condition here? The limit has to give me the exact same value. So what am I saying? The exact same value as the function. 2 and 3 are not equal, right? So what we can say right now is that statement, the limit of x approaching -1 in this case, for the function, a g of x in our case. I'm getting the name from here. Is not, so I'm going to put it a not equal sign to f of -1. What does that mean? Therefore not. Therefore, the function is non-continuous. I should have put a statement more like this. 4. Does that make it some sense? 1, 2, 3. Now, I didn't bother with the picture for the first one, because I think you're familiar, but maybe not. If I had a graph here for this one, at -1, you would have had an infinite, right? And you would see, okay, definitely not continuous. Any variation, so if I had a function like this, you had like this, and then this at -1, you'd say, okay, definitely not continuous. With the picture, you'd say why, right? Infinite discontinuity there. Therefore, not continuous because it doesn't even exist at f of -1. And even if you had this scenario, I think you'd still come to the same conclusion. Or both were going down. That doesn't need to confuse me. What would g have looked like at -1? Well, you would have had some portion of a quadratic, right? So basically what you would have had is basically, I'll just draw a quick sketch here. As long as you had, you would have had a hole like this, right? And then a dot right there, and 2, I didn't make it to scale or anything like this, but in this case, the hole was at 3, a height of 3, and g of -1 would be at 2. So this is what I'm representing here. This is representing this limit from left to right. It comes to this hole. Do you see what the picture of that would look like? Now, I could have given you the picture of this function with enough grid lines or something that you could have read that. Without the equation, you'd say, okay, g of -1 equals, and you'd trace it over to 2. You'd have enough. Then you'd say, well, the limit from the left, from the right is approaching the same value. That's 3. It's clear here from the picture that it's not continuous, but you'd still give me the 1, 2, 3 reasoning, right? 1 and 2 are, those conditions are met, but the limit does not give you the same value as the function. There is a way, so don't just assume piecewise functions aren't. What if this dot here, this x equals, well, x, g of -1 equals 2. What if I had defined it right in there and put it at 3, right? Then this would have been continuous, right? If I just stated right here that this was 3, I've created a continuous function for that piecewise function. So don't assume piecewise functions are not continuous. Back to H, C. Well, h of negative, I'm writing F on my page. -1 belongs to the first category, so I'm going to just evaluate -1 minus 3. So you do the arithmetic with the signs. -1 minus 3 is -4 inside the absolute value. So that's 4. Good enough then. That's the first condition. We tested it. Second condition. Does the limit exist? From the left to on the right. This is absolute value, so I'm going to be careful. I'm going to use a left and right, because I know something might be up. X approaching -1 from the left for this portion of the function. From the left, you got to use x minus 3. I'm going to pause for a second here. -1 from the left. Why did I choose that? Because x, when you're using -1, it belongs to that category from the left, right? It's things smaller than -1. I got to use this portion. When I use the right-hand side limit, I got to use this. Make some sense? Why? Because it's x is slightly greater than or way greater than. Okay, so back to this. I can look at this and I could think, yeah, there's no use using -1.001. It's basically the same as -1 minus 3. So that's going to give me 4 from the right. The limit from the, I said from the right, my mistake, from the left. x approaching -1 from the right uses the other equation as we, because it's in this part of the domain. I can plug it in. -2 plus 11. 9, right? You see that the left and the right limits don't match? Okay. So then that means the limit doesn't exist. The limit of x approaching -1 for the function h of x is undefined. Therefore, h of x is not continuous. Okay? How would that look as a picture? And that portion as a picture here, 4 and 9, I'm only focusing on the -1 portion here. Well, from the left, and it was inclusive, wasn't it? Yeah. It'll go up to 4. And at 9, it would start there, but it wouldn't actually include it, right? I'll make that look more like a hole, like Marcus fat there. So this is a jump discontinuity, where the limit doesn't exist. It's from the left, it approaches a different value from the right, so we don't even have to test the third thing. The limit doesn't exist. So look out for that if you're giving it pictures. Now, I will assume you can identify them from the pictures of the graph. So a little practice if we've got the equations given. So as soon as you're looking at this, you're thinking, where could the possible discontinuity happen? At the, what are you guys thinking is the possible spot where you're going to have trouble with this function? Oh, come on, guys. What's a value you couldn't plug into this? 2. So if you're given a rational, look at the denominator. It's the most likely spot. Basically, all of these are rational. This is probably a problem spot. Here, problem spots, and this spot is a possible problem spot, right? Okay. You look, and sometimes they are, sometimes they aren't for piecewise. Okay, back to the A. So, with A, x can't equal -2. Can you guys just tell without even trying to graph this, what kind of, is it a jump, is it infinite, is it removable? When you're dividing by 0, you would have like, I said -2. Why don't you guys stop? 2. What kind of discontinuity would that be if you graphed it? Infinite, right? You'd have a vertical asymptote. So I can categorize this as infinite. For me, you can write DISC, discontinuity, but state this at x equals 2, okay? So this is what I'm looking for in an answer, the type and where. Some functions have 2 or 3 discontinuities. There's possibilities. Now, right off the bat, you see this. So I'll check that out. -1 looks like the trouble spot, right? So x can't, that's a domain restriction. I don't know if that's infinite or not. On A, I could see clearly that x minus 2 and x don't have any factors in common. Now, you might not remember it, the formula, but do you remember that there is a formula for x cubed plus 1, a sum of cubes or a difference of cubes, and it involves x plus 1 as a factor. Now, I'm not requiring that you memorize that because it's no longer part of the high school curriculum. So, something like that, I'd actually probably use a quadratic to do a question like this. But for instruction purposes, I will just give this here. Since f of x is equal to x plus 1, x squared minus x plus 1. If you multiply that out, that's x cubed plus 1. So I'd give you something that you would be able to factor, or maybe I'd give you a factored form. What does this tell you? What kind of discontinuity is the negative one going to give you? It's going to look like a hole, but with the name we give it is, because you can removable, yeah. So I'm going to say removable discontinuity at x equals negative 1. That's the kind of answer I'm giving you. And if you had it on a picture, you'd be able to show. Now C is more like it. Can you see with C? What do we got here? Well, negative 5 is a trouble, or positive 5 is a trouble spot. Can't have that. So we'll look at this. Can you see that you could factor the top? I'd have to think about this a little bit. But if we had f of x, I hope you could factor this, x minus 5, x plus 4, looks like you could remove that, right? Kind of. Kind of. What would happen if you were just slightly under? Like 4.999. Now, 4.999 for this, no grief. 4.999 plus 4, it'll be close to 9. So that's not a problem, it's going to be positive on that one. But let's just examine this part. If you had 4.999, we'll just say 4.9 minus 5. What do you get? A negative 0.1, right? Negative, right? So you'd have negative 0.1 here. You'd have something close to 9, but it's positive there. And negative 0.1 there. Do you see that the top, because it's in absolute value brackets, come out positive, right? So you're going to have something that gives you, well, I'm basically evaluating the limit right now. I'm just thinking about it, though. It's going to give you a negative 9-ish kind of thing. Do you guys follow me on that? Maybe, really. What if I had 5.01 or 5.1, just for easier math? I'm going to get 5.1 here, minus 1, or minus 5 is decimal 1. So I'm going to have a positive times a positive here. Here, I'm going to have decimal 1 positive. I'm going to get something that gives me something close to positive 9. Do you see that it looks like it's removable at first? Don't. Just think about this absolute value thing. You can use your calculator, type some things in or something. It's actually going to be a jump. Okay? You guys see why? You got to think about it, and you got to, if it helps you, plug in some values. But that's why. So you could formally do the limit from 5 approach from the left, 5 approach from the right, and then see that. I'm just doing it quick because I'm running out of time. Then D. There's a possibility of 3 to check out, but you know what? For time reasons, I've shown you a little bit of each. I'm going to skip that one, only because time reasons.